Welcome to a lesson with Dr. Powell. Let's suppose that we have a function that we want to find a minimum value of, um, and this function has three variables in it. Well, how does this, and we're going to subject to a constraint. Now, how does that work? It's the same way. That's a z, excuse me. It's the same way as before with the level curves, but only we're dealing with level surfaces now. And we want to know when different level surfaces are tangent. So our restriction, what if our restriction is a level surface as well? So we have a level surface and another level surface. We want to know when those level surfaces are parallel to each other, so that because level surface represents of this function represents a value of it. And if you want to just touch a value, then back away. That's the same thing as taking another level surface and just kind of being tangent to it. So let's suppose that we want to minimize this. This is kind of similar to minimizing the distance a point is away from the origin. If you minimize this, because you'd be minimizing that as well. So we're kind of minimizing distance from origin, but let's just do this way. It's a little simpler to think of just the without the square root. So just like that. Okay, cool. All right. So in order to do that, let's get our restriction to. Suppose our restriction is y squared minus z squared minus 2 is equal to 0. All right. So let's see how we can work with that. So, well, for instance, let's just make this our constraint function, and we're looking at a level surface of it that we're restricting ourselves to. All right. So we're going to make sure we're staying on this level surface, but we also want to, so this will be one of our required equations for our points x, y, z, but we also want these two gradients, the gradients of these to be parallel to each other. So we have delta f, we want to be equal to some scalar multiple of, so gradient f is equal to some scalar multiple of gradient g. All right, so doing this, let's see, we'd end up getting 2x, 2y, 2z. And this one over here, we'd end up getting 0, 2y, negative 2z. Okay, so we have 4 equations and 4 unknowns, because we have this equation right here. Okay. Now, okay. So in particular, we can check a couple options. Notice that, okay, let's see. Right, okay. All right, so we can get, let's just write out the equations. So the equations we have, 2x is actually equal to lambda times 0 is equal to 0. So we know x has to be 0. That's just a given. Okay. Let's see. We also have 2y is equal to lambda 2y. Okay. So if y is not 0, we know that lambda will have to be 1. Okay. So if y is not 0, then lambda is 1. So those are mutually exclusive cases there. And we also have a similar thing here. 2z is equal to negative lambda times 2z. Okay, which actually tells us if z is not, so if z is not 0, so we can divide by it, then lambda will be equal to negative 1. All right. So, all right, so it looks like if, okay, so if y, so and this is interesting, because if y is not 0, then that tells us that z has to be 0. Because if z weren't 0, then that would contradict this statement. So z would have to be 0. So really, If y is not 0, we end up having the case that z has to be equal to 0 here in that case. Okay, so and if z is okay, so we have but if z is 0, let's see what y would be. So if z is 0, then y would just end up being the square root of plus or minus the square root of 2. So we end up getting plus or minus the square root of 2, 0, and x has to be 0. So we end up getting this for that case if if y is not 0. Now, what if let's see here. Okay, so that's great. Okay, so what if then, so we get those points. Now, what if z were, now if z is equal to 0, then okay, that's what we have. But if z is not 0, then y would have to be 0 because otherwise, okay, so if z is equal to 0, let's just write out the logic. If z is 0, then that's the only time that you can actually have lambda not being 1. So let's see. Okay, so if z is not 0, that's what I mean. Okay, if z is not 0, so that this was the case when z was 0. If z is not 0, then lambda has to be -1, which means that you can't have y not being 0 because that would require that lambda is 1. So that would mean that y is 0. Okay, so that we have to treat that case. So if y is 0, what happens? So if y is 0, then we end up getting, so if y is 0, then we end up getting negative z squared is equal to +2. Well, that just can't happen because that's a negative and a positive there, and that just can't work. So therefore, that case can't occur. Okay, so I think we've covered all our bases for cases. This is really the only thing that really can work to making these equations satisfy. And we can check it in this parallelism to see if it really works. So if x is 0 and y is 0, of course, this holds. And if y is plus square root of 2, yeah, that definitely holds, and it's a scalar multiple. So we're well on our way. It looks like this this is good because this satisfies this equation, but it also satisfies this equation up here. So we've done our work on finding the 2 points that are parallel, where these are parallel. Also, on this, we can see that this is a nice function, and right, okay, and it's continuous on there. Okay, so let's just see what this will be and see what we get. We also know that this function is bounded below, so it's continuous, and it's bounded below because it can't, I mean, in particular because this function isn't negative, so it's bounded below by 0. No, it's going to bottom out somewhere. In fact, if we were to, so this really should represent some kind of minimum. If we put in a square root of 2 into this for y and zeros for x's in here, we'd end up getting just 2. So that tells us that the closest that any point on this curve is to the origin, because we minimize distance, is yeah, actually is the square root of 2 is the closest distance. Square root of 2 is closest, but the minimum value of this function itself is 2, but the closest distance is square root of 2 if you take the square root to find the distance. Thanks for watching.